So today, let's continue with the topics about singly linked list. So last time we introduced about the idea. Let's review very quickly how you can do this in Java from the most basic level. And today we're going to show you how you can trace and define certain methods that are fundamental. And then you'll be expected to do something that's more to extend the singly linked list. Okay? Let's see how the code structure looks like in Java. So we got two classes you have to worry about, two classes. The first one is called node. Remember, basically a linked list is simply a chain of linked nodes. Each individual node is defined as a node class over here. So we have node over here, and we have basically two attributes over here. We got string name and also node the next. For this particular illustration, let's assume we only store string. Okay, it can be integer, or it can be double, or it can be person, but just for string. String is a reference type. And then you can see for this one here, this one, the next reference is what's really new to you. So that one means the node is going to point to some other nodes. Otherwise, it would just be null. Okay, the default value for null, for the reference value, will be just null. Okay, and then we have the constructor over here, which means you got to pass the element that's going to be stored for this particular node, and also its neighbor. And its neighbor may be null. Okay? And then you simply do the simple assignment like this. And you have also the getter and setters for the elements. You also have the getter and setter for the next. Okay? So that's about the node class. Any questions? Just about the node. We don't have to extend this node class anymore, I don't think. We only have to extend another class, which we didn't talk too much about last time. But let's focus on this particular class this time. The second class is called singly linked list. And for this class over here, it has a special attribute called head, which means the head, the front of the list, which is going to be a single node. Okay? You can see that. Let's try to compare a little bit different. Think about the preparation exercise you did for lab test number two. When we talk about the birthday book, we got an array of entries. In that case, you have the entries which we initialize to be maybe of size 30. You know the size already. But now, in the case of the singly linked list, you don't know about the size. And the initial head will just be null, which means the head points to nothing. Okay? I'm going to draw some diagram to show you. Okay? And then we are going to show you different methods that you can define on the singly linked list. That's something we're going to focus on today. We're going to just go a series of methods. You can add something to the first of the list, and you can also try to remove the last element from the list. You can also add at a particular position. Okay? We're going to go into it. Okay? First of all, any question about how we define the two classes over here? As I said, the node class is pretty much assumed already. So you are always given this node class. It's pretty much, excuse me, it's pretty much it. But for the singly linked list, we have to define that further, much further today. That's the focus. Okay, if no question, let's go on to the next one. Okay, so we talk about approach 1 and approach 2, right? So you should really know how to construct a list differently, right? You can either try to go backwards, as we said for approach 1 from last lecture. And at the end of the lecture, we also try to do approach number 2, right? You can just create 3 nodes over here with their neighbors just be null at the same, to begin with. And then you can set their next to be the corresponding nodes, right? So whichever you prefer, okay? Okay, let's see the first method for our singly linked list. From now on, let's assume the following. When we talk about any method for the rest of the lecture, we assume we're going to define the method inside the context of singly linked list. That's the method we're trying to support, okay? And then the only attribute we have for now, we might add more attributes later, but for now, you only have the head of the node, okay? Head of the list. Let me just show you one more thing. It's really important to realize the following, okay? So now let me just go to the iPad and then show you something here, okay? So you have to know what does it really mean for an empty list. Okay, add page below. Okay. So now sometimes I'll just say singly linked list, SLL, just for short. Okay. So what does it really mean for a singly linked list to be empty? What does that mean? So now let's say if you go back to the definition here, we don't have the constructor here, but I'll add it later. So this is what you can expect. You can say SinglyLinkedList, I'll say list. It's assigned to a new SinglyLinkedList, like that, just empty. So what does this do? So this one should create an empty list. So what does empty list really mean? That means the head simply point to nothing. You just don't have the head yet. So that means the head is simply equal to null. Just that. Okay, let me just visualize that. So this is what you can have. So you have list over here, and then it's going to point to some SinglyLinkedList objects over here. And then the only attribute we have now is called head. And then at the moment, it's simply going to point to null. Okay? That's what it means to be an empty list. Okay? So you still have the list objects over there. It's just that the head attributes points to nothing. Okay? So what does it really mean when you have a list of size 1? Okay? Let me just show you a little bit preview of what we're going to say. Let's say I'm going to use a different color here. What about I say list dot add first? Let's say I want to add Alan into the list. What does that mean? Let's try to visualize what's going to happen first before we talk about how you can define that. So what this will do, first of all, it's going to create a new node, right? I'm talking about different class, just a node. And the node, remember, every node has 2 attributes. You got elements, you got next. Element here, and also next. The element is going to point to some string objects, which will just be Alan. And then the next, for now, it's just alone. It just be null. So far, you can see the newly created node has nothing to do with the list itself. So what it has to do as well is to say the head is going to point to this particular node. Any question until now, the green part? So the green part does 2 things. We first create a new node, which points to the Alan, the new elements. And then we let the head of the list point to that particular node. Okay? Let's try to do one more method, and then we'll see how we can do that. I just want you to get some intuition first. Okay? Let's say I have also list dot, let's say add, again, first. This one will be interesting to see. Let's say mark. You know what? Let me use a different color so you can really see that from the notes. Okay. How about blue? Okay. So let's say you say list dot add first again, and over here you put mark. Let's try to imagine first what's going to happen here, visually speaking, before we draw it and also before we see the code. Okay. It's not too complicated. addFirst simply means whatever name you're going to pass as input is going to become the first node after you call this method here, right? After we say list.addFirst Alan, Alan becomes the first node in the chain. So now if I say addFirst Mark, who should become the first node in the chain? Mark. And who should be the second? Alan. We should not lose with the existing chain. Okay? So what we should expect to see is as follows. We're going to create a new node somewhere here, and then we're going to say the new node's next is going to be the current head of the list, which is a green one. And then we're going to set the head of the list into the blue part. Okay? I'm going to show you exactly how that's going to happen. Okay? So somehow, if you are going to support any new methods for the SinglyLinkedList later, the best thing you can do is to draw a diagram first to understand what's going on there, rather than thinking in your mind. Okay? Let's see how we can draw the diagram. First of all, as I said, we're going to create a new node over here. And the new node is also going to be of type node. And also it has elements, it has next. As we said, the element should be mark. It's going to point to mark. And then its next is going to point to whichever the head, current head is. So it's going to point to this green node object here, right? One more thing to be done. You can see that now we got aliasing. You can see now, for the moment, we got list.head, which points to here. And also, this node.next also point to this node. That's not what we want. Okay, we want a single chain linear structure. Okay, so what we should also do is to say, now the head should not be pointing to the green node anymore. You should point to the blue nodes. So now again, we got a linear structure that's updated. So now you can see list.head, the element is now marked, not Ellen anymore. And list.head, the next, the elements will be Ellen. Any question about visualizing addFirst? We'll see that how we can implement that. It's only a few lines of Java code, so I want to make sure you get an intuition first. Okay? Questions? Okay. Okay, let's now see. The first one I would like to go through first is counting the number of nodes. Again, we are defining all the methods in the context of SinglyLinkdedList. Okay, so we always have the head available. So now let's say we do a method called getSize. It's an accessor. So this accessor method here is going to tell us how many nodes are there in the chain starting from head, right? For example, if you see over here, let's see one example here, and then I'm going to illustrate that. So you can see this chain of nodes. We're starting from the head over here, and then you can see we got 1, 2, and 3. We got 3 nodes in total. So when you say list.getSize, it should give you 3, right? So now in this case, for this particular example, if you say list.getSize, it should give to you returns 3. That's what you should return. Okay? Now we should see how to do it, right? Let's try to understand what this code is doing. I think the first one is really important because you're going to reuse part of it quite frequently, almost for every method for the SinglyLinkdedList. Okay? Let's think about what the idea is. Okay? Let's see what's really straightforward over here. Let me just start from the simple ones. You can see inside the method, I'm declaring a local variable called size, initialized to be 0. And then somehow I'm going to increment that inside the body of some while loop. Eventually return the size. So this part is very straightforward, right? Because you want to get a size. But now, how do we know how we can update the node, right? And update the counter. That's the critical bits. So here comes the critical line you should really pay attention to. So we declare some new node over here, and then the node is simply called current. Guys, please. Okay. In line number 3, we have a new node object here called current. Okay? So this is really critical, current. Let's say, how do we draw the diagram for line number 3? What does it really mean? When we say node current is simply assigned to head, what does that mean? Are we copying only address, or we're copying the contents of head? Apparently head is this object here, right? This is head. That's the object that's being pointed to. When we say node current is assigned to head, what are we doing here? Assign the address, right? Copy the address, which means we have another variable just called current over here, and then it is assigned to the address of this particular object. So now it's pointing to there. Okay? Let's call this 1. This is 1. Okay? Now, we are now entering some while loop in line number 4. And you can see the state condition, which means as long as this condition is true, we're going to stay in the loop. It says that the current is not equal to null. So what does that mean? So that means as soon as the current becomes null, exit from the loop. Right? So I simply just take the logical negation of the condition there. The condition means as long as it is true, you're going to stay there. So which means as soon as it becomes false, you're going to exit from the loop. Okay? So now let's see how that's possible. Okay? You can see that now the only line that we haven't discussed so far was line number 6. Okay, let me use a different color. Okay? Line number 6 over here is, this is line number 6. Okay? I briefly talked about line number 6 last time, but let's do it again. What does that mean? Okay? I'm going to write it over here. When I say currents is assign current dot get next. Okay, what does this line do? This is for the very first iteration. Okay, current is assigned to current dot get next. Why don't we figure out what's current dot next? What's that? When we say current dot get next, current is over here, right? Current dot get next should give us the address of this next node object, right? And then we're assigning this address to current. We're replacing itself with some updated value. This is really important, okay? So what's the effect of this? Let me call this number 2, okay? Number 2 simply means current, rather than pointing to this leftmost node, it's going to move itself conceptually from left to right by just one position. And then current is now going to point to over here. That's number 2. Okay, I'll pause a little bit for any questions you might have. That's a very critical step. And we're going to keep doing this until current becomes null, which means we should not go any further. Okay? Guys, any questions? You're going to see this kind of pattern a lot for the linked list, because the only way we can judge if you're reaching the end is to see if the current is null. That's a typical way of doing it. Okay? Okay? If you're okay with this, let's continue with this. Okay, so now, after this, we're going to also say the size is going to be plus plus, right? And size was initially 0 over here, and then we're going to increment the size becomes 1. So this means we have traversed so far 1 node from the list. That's why it has just become 1. Okay, let's do one more. Okay. And then after size plus plus, we're going to go back to the while loop, right? Go back there and check again. Now, current not equal to null. Would that be true or false? Should be true, right? Because current is now the pink one. The current is pointing to some node. Of course, it is not null. So that's going to be true. So I'm going to go over again. Okay, let me use again a different color here. What about red? So now let's use maybe green. So now what we'll do is another one to say current is assigned to current dot get next. Okay, that's number 3. Okay, so what this will do, again, what's current dot get next? It's simply the next node. It's relative to what current is pointing to, because current is really the pink arrow over here, right? So now current dot next is going to be the address of this object over here, right? So now when you say current is assigned to current dot get next, so rather than pointing to over here, it's now going to point to over here. Right? That's what this will do in the second iteration. And then it's going to increment the size even further. So now size becomes 2. So size becomes 2. That means we have now handled 2 nodes in the list so far. Only 2 nodes. So size has, but we are not done yet. Because now you can see the current is still pointing to some node, which means it's not null. So now we go back again to the header of the while loop and check again. When we say current not equal to null, would that be true or false? Still true, right? We haven't reached it in the end yet, have we? Haven't. So now let's try one more. Let me just choose one more color. That should be the last one. What about just gray? Okay, over here. So now you can see that it's now pointing to this node particularly. So now current not equal to null is simply true. What we will do is we'll do one more. We'll say current is assigned to current.get next. Okay, I'll just get next. So what would this do? Again, what's current.get next? Again, it's relative to where you are for the current. Current is now the green one. Current.next is going to give you null, right? So now we're reaching the end. The loop has to end eventually. So now this will just give you null. And then we assign current to null. So that means current is now pointing to just null. And then we're going to increment the size for another time. So now size becomes 3. So this means so far we have traversed 3 nodes in the list. Okay? Now what's to be next? We're going to go back to the header of the loop over here, and then what's current now? It's null. Null not equal to null, false. So we exit from the loop, and then return the size, which is just the last value we just reassigned, which is 3. Okay, this is a complete walkthrough of the getSize method. You will see that the way we handle many other methods in the rest of the lecture will be very similar. Okay, make sure you get this one first. Okay, any questions? Is it clear, or you're just lost? Okay. Assume silence means okay, right? Okay, good. Yes, go ahead. Yes, yeah, I'll take yours later. Okay, here, press. Okay, every time. Okay, that's a very good question. Okay, the question was, does that mean every time when we say list.getSize, depending on how long the chain is, we're always going to start from the head and go eventually to the null, right? So you're talking about time complexity. It's a very good question. That will be the next topic. Okay, let's talk about right away. Let's analyze the code. Code is a little bit polluted right now. Why don't we go back to the slide, which is clean. The same code over here. Let's say we talk about how we can analyze the complexity of a code. Let's think about what's the time complexity for this particular block of code, which means how expensive it is for client to call your method whenever they say list.getSize. William, why don't you say? Depends on how many nodes you have in the chain, right? If you got 3 nodes, 3. If you got 1,000,000 nodes, 1,000,000. Huh? N times, exactly, linear. Good. So that means this is a linear operation. Now, let's try to make some connection here. Given an array, how do you get the size? Array dot length. That one's a constant operation. You can see this one is much more expensive. However, we'll show you in just a moment, but this is how we can do from scratch. You can somehow trade space for time. I'll explain what this means in just a moment. But for now, that's the best we have. Okay? Did you still have questions? Go ahead.
I was just wondering, if we wanted to replace it with generic objects.
Let's not worry about generic just yet. Okay? We may cover generics when we talk about inheritance, but not for now.
I meant the object class. I don't know what generic is, so I'm not sure.
So what do you mean by generic?
No, I meant the object class.
Oh, you're saying that we simply put objects over there as the, oh, okay. I'm not sure if this is what you meant. Let me try to see. Was your question something like this? Let me just go back to our class definition here. You're trying to say, now for the element, rather than string, you're going to put it objects. I would say it's a bad practice. I'll try to explain to you why, maybe when we talk about inheritance. How about it? Just bear with that. Okay? For now, let's assume that's string or integer or some particular type. That would be the preparation exercise I'll give to you. So you can imagine that the preparation exercise for lab test number 3 would be, let's now try not to have an array of entries. Let's try have an array of, let's try to have a linked list of entries. And how would you redefine all the other methods? That will be the preparation exercise. But we'll get there, don't worry. Well, you just finished that, right? Number 2, so we'll get there a little later. Yes? Can you rotate linked list clockwise and counterclockwise? That will be, I can give that to you as an exercise as well. Yes, definitely you can. Okay, since you talk about this, I'm actually happy that you asked this. It's not difficult, okay? Let me give you some idea. Add page below, okay? Thank you. Good. So now let me try to add it back. I believe I have that in my photos somewhere. Good. Okay, let's say that's over here. Let's say we still have this list over here. Let's say rotate to the left. Okay. Let's say we say list dot, let's say shift to, okay, let me just follow Java notation, shift to left. Okay, what does it really mean? Use your imagination here, I'm gonna draw, okay? Shift this to the left, which means the leftmost become the rightmost, okay? So what you will have is something like this. What you will have is the head. So now the head is now going to point to this node instead. And the next over here is going to point to this one over here. And then the next reference should be discarded over here. Okay, well, this is just a sketch of the idea how you can do it. This is a little bit more advanced, but since you asked, I just want to share with the class. This is something you definitely are expected to do for lab test number 3. Okay, just to give you some idea. Okay, but don't worry, I'll give you some preparation exercise so you know exactly what I expect. Okay, but my number one advice is for linked lists, when you want to define certain methods that you may not have heard about or thought about before, the best way to do it, draw a diagram. That's the best way. I will do the same. Okay. Okay, that's about the getSize method over there. And also we talk about for getSize, the complexity is simply linear. Okay. Oh yeah, go ahead.
For shift left, could we do it similar to the remove entry? Where we run a for loop, set here's the I, here's the I.
It's a very good question. I would say it's doable, but it's overkill. Here's the intuition you should get. So think of whatever operation that might be expensive for array is in principle cheap in the linked list because they're fundamentally different. Array has absolute position over there. That's why if you remove the first one, you got to shift everything to the left. But for the linked list, it's simply just references, right? The next reference. As long as you set the next reference properly, you're fine. Okay? Hopefully you will build more and more intuition about it later. Okay? But that was a good question. You can do it, but it's overkill. If you could do it constant time, why not do it? If you could do it constant time, why would you do a linear time, right? Okay. Okay, that's about getSize. Okay, let's move on. Guys, really, no question, right? Okay. Okay, now, so you can certainly try to follow this table here. That's exactly what I said. You know, this one just written form of what I just traced. Now, let's try to see this one here. I can still draw some diagram to you for this one, but maybe not as detailed as before. Let's try to see how that goes. Okay. Now, let's say this. Now, we're going to do a very similar method over here. And I'm going to fix this. This is a typo. There should be no parameter. Okay. We just want to get the tail. Remember, the only attribute we have in the SinglyLinkdedList is just the head. Given the head, how can we get to the tail? Well, it's actually simpler, right? We don't need the integer size counter anymore. We just want to keep going until the current becomes null. All right? Okay. Go ahead. This one here?
Yeah.
No, actually, there should be no parameter. Remember, every method we are defining now, they are in the SinglyLinkdedList. Right, don't forget. Yeah. Okay? So now, again, I'll fix the typo. Okay? Just make sure you understand this. There should be no parameter over here. Okay? So now let's see how we're going to do it. So you can see that we don't have the integer size anymore. We just have the current. You can see the current is going to come out so often. You really want to understand how we initialize the current and set it every time at the end of the iteration. Now the only, and we also say the tail should be just null. So eventually we're going to return the null. Okay? So now we also have the while current is not equal to null, right? That's pretty much the same as before. We should know when to terminate the loop. As soon as we reach the end, we should terminate. And now we say, let's try to trace this very quickly and see what we get. Okay? I'm going to switch to iPad and see how we can do. Okay? So get a tail. Okay? So now let me use green for current, and also let me use red for tail. How about that? You can see eventually we want to return. You can see initially no tail is equal to null, and then every time we simply say tail is assigned to current, and then we say return tail. You will see why. Okay. So this is kind of the new bits from before. And also we have, what about the current? This is the current and also state condition here. And this is the update to the current. Okay? Let's see how the two node objects are going to play with each other, to collaborate with each other. Okay? Let's now see. Over here, you can see number one over here. For number one over here, we say that current is assigned to head. Head is pointing to over here. So current is now going to point to here to begin with. That's number one. Agree? As before. Okay? Now, what about the tail? Tail is going to be just null. The tail initially just going to be null. Okay? I would say this is 2. That's what we have, just from line number 2 and 3. When we get to line number 4, what does that mean? We're going to compare where current is currently pointing to, not equal null. Guys, if you want to talk, would you please talk outside? It's really distracting to me. Right? Okay, so now let's see this. We have null over here. So now from step number 2, tail is pointing to null over here. For line number 4, when we say current is not equal to null, what does that mean? Current is now pointing to an object, okay, which means it is not null. It's pointing to here. So that means this one over here should be true. It is not null. Okay. Let's get on to line number 6. So what does that mean? We say that tail should be pointing to wherever current is now pointing to, right? So we're going to copy the address of current at the moment into tail. That means tail, rather than pointing to null, is going to point to over here. Okay? So that's number 3, let's say. Number 3. Okay? So far so good? So now you will see that what's going to happen is tail is going to be one position behind current. You will see what that means in just a moment. Okay? So now what about this line here? And we have number 4 over here. We got current is assigned to current that get next, exactly the same as before. So what we want to do is, now current is going to point to its next. Okay? So this is number 4. Okay? And then what we'll do is we'll go back to the beginning of the while loop, and then current not equal to null. Of course, it's not null. That's true, right? It's pointing to over here, a different node. And then we're going to say that, now let's see what's going to happen. At this moment, you can see current is pointing to this node over here, whereas tail is pointing to one node just behind that, right? That's some kind of the thing we are trying to maintain. Okay, let's now run the second iteration. We say that tail is going to be, let me call this number 4, okay? Number 5. Let's call this number 5. Number 5, we're going to say tail is assigned to current, which means tail is going to point to not here anymore. It is going to point to over here. Okay, so this is number 5. Okay, let's try more. What about the next one? This is number 6 over here. We say current is assigned to current that get next. So now current is not going to point to here anymore. It's now again going to move one position behind. Right? So now this is number 6 over here. Again, we have the green arrow and the right arrow, one position different. Okay? Now we're almost done. And then we just go back to the loop again. So now current is now pointing to over here. So we are still not done yet, right? Because it's not null. We haven't reached the end yet. So that means we're going to go into the loop. And now we have over here 7. For number 7 here, again, tail is going to point to where current is pointing to, right? So now tail is not going to point to here anymore. It's now going to point to over here. Okay? And then what's really left is we're going to say over here, number 8. And then we have current is assigned to current that get next. Okay? So now current, again, is not going to point to here anymore. Okay, let me say it's now going to point to just now, right? Now over here, right? So this is number 8. I think I forget to say this is number 7. Okay, just for your reference. So now what's going to happen is, because always the green one is one position behind the red arrow, which is the tail. Now you can see the green one is exactly now. That means the red one should point to the tail we are looking for. Okay? So now if you go back to the loop again, you can see the current is now pointing to a null. So that means null not equal to null is false. What do we return? The tail over here. That's exactly what we're going to return. The tail is currently pointing to this node here. So that means this is the tail. It's kind of a tedious and kind of error prone to trace, but I think it's really important for you to understand. On a small example, line by line, to see exactly how things go. Because for the more complicated methods, you might just have to do more. Okay? Any questions about this? Yes?
So, this example should take it to what?
No, this one here, we're only getting the tail. We're not trying to shift anything.
We were only getting the tail.
We're only getting the tail. Remember, in line number 9, we just return wherever tail is currently pointing to, right? So we only return the tail of the list.
So, like, initially we start with tail equal to null, and
Yeah.
then at the end, tail is equal to the last element.
Exactly, and then we return that reference, which means whoever called this method here, getTail, they're going to get also the reference of the tail node over there, the last node. Okay, how about I do one, let's say, keep this example here. Let me try to make sure let me try if I can make you understand a little bit more, okay? Let's say this. Let's say we got this list over here, okay? So now, for example, let's say, if I say list, okay, you can see that, right? If you say list.getTail. Okay, let's try a few assertions, okay? Let's just try to tell me what the value should be. If I say list.getTail dot get next, what should that be? I heard null, right? Because list.getTail will give me exactly the address of this node. And that node.getNext will give me just null. Intuitively, it makes sense. It's already a tail of the list. Go to the next, it should be no. Okay. One more. What about list dot get tail dot get elements? What's that? Tone, right? Okay, another one more. Okay. What about I put it here? I say list dot get tail dot get next dot get elements. What is that? Null pointer exception, right? It's a trick, but you should know why. Because when you say list.getTail, it will give you this null over here. When you say list.getTail.getNext, it will give you this null over here. And then null.getElement give you null pointer exception, right? So be careful. I think from now on, you're going to run into the null pointer exception way more often than you did, because that's a typical errors. So don't be too frustrated. You're going to struggle through it before you get to 2011, hopefully. Okay? Yeah. So it could be that. This might be what I can do in lab test 3. I can say, now here is one version of the, let's say, addFirst or addLast or some getSize, for example. However, if you run the test case for that, it has null pointer exception. The question is, fix it and explain what the errors, where the error was. You know, something like that. Okay? But the reason that I mentioned this, I would want you to really motivate you to study, right? So you really want to get prepared for 2011, right? Okay, if no question about getTail, let's move on. Okay. Now, let's think about what's the time complexity for this particular method here. Should that be constant operation, linear or quadratic? Linear. Even though we don't have a for loop here, but I would say, let's think visually, right? If you have a list of size 1,000,000, how many iterations it would take for you to get to the null reference as the next? 1,000,000 times. right? So that means it's linear within some constant factor, right? So that's the linear operation, okay? On the other hand, if you want to get to the last elements of an array, what will be the time complexity? Constant, how? How would you do it though? Right, you just say array, let's say a dot brackets a dot length minus 1, right? A dot length minus 1 is constant. Indexing is also constant, right? So you can see, I would say almost for the basic operation there, that's why we are introducing the linked list as an alternative to array. What's really expensive for array, on the other hand, is actually cheap for the linked list and vice versa, okay? We'll see some comparison table at the end of the slides. We'll see that, okay? Okay, you can also try to trace this table over here, okay? Exactly what I said, okay? Okay, now, so far we talk about two methods. We talk about getSize and getTail. And these two methods, unfortunately, they are linear time, right? But these two methods are so special because you may just want to query about the size of a list or you want to get to the end of the list so often. You don't want to just have constant, you just don't want to have linear operation every time. What we can do is we can do the so-called trace the space for the time. What does it mean to trade the space? That means let's waste a little bit of space, which means we're going to create two more attributes in the SinglyLinkdedList class, which is going to make our getSize and getTail method much easier, much cheaper. I'll show you how you can do that. Okay? Okay, and this is just to motivate to say why we frequently want to get to the tail of the list. Let's say we haven't talked about queue, but queue is just in the sense you have some customer queue, like a first come, first serve. Sometimes you may just want to go to the end of the queue, right? To add a new customer. And why would you need to know about a size every time? Because you want to know if the current customer queue is full. You may just want to create a new queue or just to shut the door to say, no more service today, right? So tail and size, these are very frequently used operations we want to perform. So we cannot afford to say every time you call a tail or you call a size, it's going to be linear. It's too expensive, right? But how can we improve that? We so-called trade the space for the time, which means we create two attributes. One attribute is called size. The other attribute is called tail, right? So now we got three attributes in the SinglyLinked list. We got head, we got tail, and we got size. And let's say now, if I want to say, how do I implement getSize? Well, just return size, right? That's constant operation. And what's going to be the definition for getTail? Well, just return tail. That's also constant operation, right? But of course, it's not just happen magically. Of course, there's a catch. The catch is, we're going to see that for the rest of the slides. The catch is, once we make the tail and the size as attributes, we're going to make sure we update them when we have to. For example, if you try to add a node into your linked list, in that case, you're going to increment the attribute size by 1, right? Things like that. When you want to remove, you're going to decrement that, okay? So just keep that in mind. Yeah, go ahead.
Do we still have to go through the linear getSize and getTail?
Okay, it depends. So let me just clarify this. Before, we say that we only got one single attribute in the SinglyLinked list, which is called head. That's all we got, which means any time we want to start traversing the list, we can only start from the beginning. That's why we actually need the loops for getSize and getTail. But we know that these two operations are so frequently used, they're so important, we cannot afford to be linear. So what we do is, let's cheat a little bit. So now let's trade the size for the space. So now let's declare two more attributes in the list class. We got size, we got tail. So it's actually now much easier to return the result.
How do they get their value?
That's a good question, we'll see that. Okay, we'll see. Yes, that's a very good question, you'll see. Okay, so for example, let me just give you one example. Let's say, let me go to the iPad over here. So now let's do another page. So now let's say we now got the SinglyLinked class, SinglyLinked. Okay. Before we have simply just node, and then we have head. So now we're actually adding two things. We have the node, which is called tail. Also, we got integer, which is called size. So now we got 3 attributes over here. Let's see how we can define a constructor. It's very easy. Okay. What about constructor? Let's say SLL, singly linked list. So over here, we're going to create an empty list. Let me make everything explicit. We're going to make the head to be null and the tail to be null. And also the size to be 0. Okay, that's what we have, right? Let me just draw a diagram very quickly. So that means whenever I say singly linked list is a new singly linked list objects, what I will have is list should point to some singly linked list objects. And now we got 3 attributes for the object, right? So we got the head, we have the tail, and we got size. The size is simply just 0. And then head is pointing to null, and then tail is pointing to null. Okay, let's illustrate a little bit. Okay, let's try to add first. What's going to happen? Now, the consequence is every time you try to add or delete nodes from your list, you got to make sure you update not just the head, but also the tail and the size. Okay, so now let's try this. Okay, again, let me use, first of all, let's say list dot add first. I think that's what I did before. And then Alan. So how should we do for this one? This one here, I'm going to create a node over here, which is a node here, which has elements and next. The element is going to point to Alan over here, and the next just going to be null. Okay? And then I'm going to say the head is going to point to over here, the new head. Also the new tail, the same node. And then the size is going to be 1. Okay, that's the first add first. Let me just do one more for illustration. If I say list dot add first, what this will do is mark. Okay, so what we will do is we'll create a new node over here. So this is going to be a node. And then we have elements, we have next. The element is pointing to mark. And because that's going to be the new first, so its next should point to this particular node, right? The old head. And what should be the new head? Mark, right? So we should change the head. Rather than pointing to Alan, the head should point to Mark. Should we change the tail? We don't, right? Because Mark remains to be the tail. Okay? And then what else to be updated? Size, thank you. 2. Okay, that's kind of the catch, as I said. So, but the good thing is, now every time we say getTail and getSize, it's constant time operation. Just return the value of the attributes. Yeah, the diagram is a bit messy, but hopefully you get a point. Okay? But we'll see how you can do addFirst. addFirst is incredibly easy. Okay, we'll see that.
Do we update in the addFirst method?
Sorry, say it again.
Do we update size in the addFirst method?
We will. We'll see that. We'll get there. I'm not sure if that's the next one, but we'll get there very soon. Yes.
I have an off-topic question.
Off topic, after class maybe. About size?
Yeah, like when you put like inside
You mean over here, right? Yes, you can. The answer, okay, the question was, can you simply put int size is assigned to 0? That's fine. I think it's a matter of preference. If you put it here, that's fine. That's the initial value. I personally just prefer to do the initialization in the constructor. That's more explicit. Well, it's completely up to you. Okay, it's not completely off the topic. Okay, so now let's see this. Okay, so now let's see we have a linked list that looks like this. We want to add first. So add first is the method we're going to do now. Okay, so this is another diagram. Okay, you will see exactly how that works. Okay, so now how do we do add first? Add first is incredibly easy. You will see that. Okay, how many lines of code do we have? First of all, we do this. We'll explain in a moment. Okay, do this and do that. Do that. We're done. What do they mean, right? We only got basically only 3 lines of code or 4 lines, and it will do it. Okay, why don't we try? Okay. Again, let me use my iPad and illustrate to you. Okay, what about addFirst over here? Okay, let's say this is the list we have. We got Alan, Mark, and Tom already. Let's say we try to do the following. Notice that the input to the addFirst is a string. Okay, if I say addFirst, oh, let me just be complete. Otherwise, okay, let's say list. Let me just write it on the top. Let's say this is what we're going to do. List dot add first. What about Jim? Okay, let's see what's going to happen. You kind of imagine what's going to happen, right? We're going to create a new node, and then Jim is going to be a new head. And Tom remains the old tail. Okay, so now here I have the tail head, and also we have the tail. Okay, let me just add it. And currently, the size is equal to 3. Okay, just current. That's the current setup. Okay, let's now do line by line. Okay, let's do the first one here. 1. What does 1 do? We have seen something like this in approach number 1. Okay, last time. Okay, let's try to understand what this is doing. What it does is it's trying to create a new node, and then the node is going to store the new elements over here, in this case Jim. And then the neighbor of this new node is going to be the current head of the list. Okay, I'm pretty sure this one is confusing. Okay, I'll try to be more explicit to you. Why don't we look at the definition for the constructor? Okay, if you recall the class node over here, okay, and then let's see how the constructor is defined. We have node over here, and then we have string E, and then we have node next. That's what we have. And then we say this dot elements is assigned to E, and also this dot next is assigned to the next. Okay, so this is the relevant definition you should know. That's the constructor for the node class, which we have gone through already. Okay, let's see exactly how this line is going to do. Let me just repeat that line over here. We say that the head is assigned to a new node, and then we pass Jim, in this case, for example, and then we have the head. Okay, let's see how this method call is going to execute. Okay, it's not that complicated. Okay, let's try to see how it's going to do. First of all, what we have is we're going to create a new node. And the node has elements, and also it has the next over here. And you can see that, first of all, you can see that here, the Jim is going to replace every occurrence of E, right? So now that means the element of this new node is going to be Jim. Okay? So that means the element is going to be Jim for this particular node. Now, a little bit more complicated is the second one. The second one over here, we say that the neighbor of this new node is going to be the head. Where's the head? Over here. Right? So that means whatever head this is going to replace the next over here. That's what we're going to do. Okay? So what does that mean? Let me draw the diagram over here. So now that means the next over here. Sorry, I should have swapped the sides, but let's not do that. Okay? That means the next over here is going to point to the head over here, because that's going to be the new first, right? Okay, that's this line. Any questions just about this line? What I just walked through was line number 2. We create a new node, And then the next neighbor for that new node is the current head. We haven't changed the head yet, but we should in just a moment. Now, line number 3 is saying if over here, oh, one more thing, I forgot. Sorry, let me take it back. What we just gone through was only this part. Only this part. We forgot about this. What does this mean? We're updating the head, right? Remember, when we talk about object creation, we always do the right-hand side and then the left-hand side. So what we just talked about was the right-hand side. The right-hand side create this new node, which points to the new point to the old head, the current head. And the left-hand side tells us, now assign that new object to the new head, which means the head is not going to point to here anymore. No, it's now going to point to over here. Make sense? So this line number 2 does many things at one go. So make sure you understand. Any questions before I move on? If you understand line number 2, I think the rest will be rather easy. It's really line number 2 that's a little bit complicated. Let me do you a favor. If you don't like this line too much, let's try to be verbose. Let's try the following. What I can do is this. Node, I'm not sure if you're going to make it more confused, but let's try. Node, new node, NN is new node over here. I'm still going to pass maybe E over here, which would be, in this case, Jin. And then the neighbor, let's not worry about it, just say now. Okay? And then I would say the new node dot set next to be the current head. And then I can say the current head is now assigned to NN. So these 3 lines are completely equivalent to the green line. Okay? They are equivalent. Can you see that? Create a new first, create a node, which points to whose next neighbor is simply pointing to nothing. And then let the next set to be the current head. And then let the current head point to that node. Okay? So these 3 lines, if you prefer, feel free. Okay? You don't necessarily have to do line number 2. Line number 2 just for your convenience, if you're experienced enough and know exactly what you're doing. Okay? Okay. We're almost done. And let's see line number 3 over here. For line number 3, we say size. If the size equal to 0, remember we haven't updated the size yet. If size is 0, that means before we add the first, the list was simply just empty, right? In that case, that means we have to update the tail as well, because the head and the tail should both point to the same node, right? So that means we should also say tail over here. Okay, that's a special case. Okay, and then increment the size from 3 to 4. Yeah, the tail should be removed. So what's the question? Go ahead. Okay, why don't I undo? Okay, let's not undo too much. Okay, why don't we do it one more time? Okay, let me do it one more time, and then I'll take your question. Over here, we can say when size, if the current size before we update is 0, that means it's empty. Empty list means head was pointing to null, tail also was pointing to null. Since we added a first node, so head and tail should point to the same node, right? So now this one here, tail rather than pointing to this one here, is now, oh, I beg your pardon. In this case, is size equal to 0 though? No, so we shouldn't touch this part, right? Sorry, I got myself confused. Sorry about that. Okay, it's good that I undo. Okay, in this case, special case for adding the very first node. Only a special case. And then after that, we simply increment from 3 to 4. Okay, so that's, yeah, go ahead.
My next question is, okay, let's say you call that and you build up like 4 sizes. So how do you overchange? Like if you say you
Oh, okay, very good question. When you only add to the first, do you have to change the tail though? You don't have to, right? You know what? It's interesting. You only change the tail when you add the very first node. Let's think about a symmetric operation. Let's say we want to support another method called addLast, not addFirst. Whenever you're adding a last node, do you have to update the head? Only when you're adding the very first node. Only, okay? Symmetric, okay? Okay, any more questions about this method here? Yes, I forgot about you.
The first person you put in,
Yeah.
you assign the tail to him and you never touch the tail again. Like we,
Yeah, if that was the case. But in this case, we just have let's assume we have some initial setup with 3 nodes. And how do we add the first into it? Yeah. So initial setup was we got head pointing to Alan and tail pointing to Tom. That's the assumed setup. Don't worry about how we get there. Yeah. Okay. Okay, now, next question. How efficient is this method? Well, complexity. Constant, linear, quadratic, exponential? Constant, right? Okay, good. Right. But now think about how you will add first into an array. Linear, right? Assuming that the array has been filled up from indices 0 until the last. If you want to add first, you got to shift everything to the right by 1 position. So you got the first slot available. But the shift operation there is going to require a loop, which will be linear. Okay? Now you can see again, what's cheap for linked list is actually expensive for array. Okay? So you really should judge when to use linked list and when to use array. Okay? Okay, if no questions, I'll go on. Okay? Now, even though I said your homework, but let's discuss that right now because that's quite important. Okay? So now I think we have built up enough such that you can just finish the rest of the slides, but I'll just go through as much as possible. Okay? Now, I want you to think about, let's think about these 2 methods, remove first and add last, given what we have. Let me tell you again what we have. We have got, in the SinglyLinkdedList class, we got head, we got tail, we got size. These attributes are available to us. For every node, we got element and we got next. Okay? So these are what you're given. Think about how you are going to implement remove first and add last. Remove first means remove the first node, right? Add last means adding a last node as a tail. Now, why don't you think about it for just a moment? Okay, give me 30 seconds and then I'll ask you questions. Oh, not yet. Think about it. Okay? Take the opportunity to think about, visualize what's going to happen in your mind. For 30 seconds, and then I will ask you questions. Okay? So now, first question number 1. Do you think these 2 methods are going to take the same amount of time, big O-wise? Question number 1, yes or no? Yes, if you think these 2 methods are equally efficient. No, if you don't think so. Yes? Oh, I'm happy, because all of you are wrong. Oh, no, they are not the same. No. One is more expensive than the other. I think, oh, maybe I'm wrong, right? No, wait. How would you do remove first? Maybe I think I want, what I want is remove first, okay, and then add last. Do I have another one? Remove last. Ah, that's really the question. I really, again, sometimes I just get confused myself. Okay, now consider 3 methods. How about that? Okay, we got addFirst, addLast, and also removeLast. That's the method I really want you to think about. Okay, right? Okay, now we got 3 methods. 3 methods. remove first, add last, and also remove last. We got 3 methods here. Okay? Do you think these 3 methods are going to be equally efficient? Okay, that's good. That's the right answer. Okay? Good. You guys are much better than I thought. Very good. Good. Okay, so now, out of the 3 methods, which ones is the most expensive? Remove last. Why is removing the last expensive though? Okay, I say that again. You know before the last. First of all, think about how would you remove the last. If I want to remove the last, I somehow want to set the tail to be the second last. How do I get a second last? Well, I got a traverse, right? Now, since we talk about SinglyLinkdedList, SinglyLinkdedList means there's no way back. You can only go forward, but you cannot go backwards. So the only way you can go to the second last node is go through a loop. And as a preview for 2011, for the remove last, we know that it's going to be a linear operation because you got to go all the way to the second last, which is n-1, which is linear. But in 2011, you're going to learn about something called doubly linked list, in which case the only extension you make is to say, for now, for each node, not only that I got the next node, next reference, I got another thing called previous. Okay, just as a preview, but don't worry about it. Doubly linked list is not required for this course, but I just want to motivate you. Okay, guys, since everybody got it, right? So now, again, sorry that I got myself confused, but remove first and add last, they are equally efficient. It's constant time, okay? But remove last is actually fundamentally different because somehow when you want to set the tail to be the second last, you don't have a straightforward way to go there. You gotta use a loop, okay? Good. Okay, so now, let me just briefly mention this. This one is going to be very similar to what you did before. Okay? So now let's say we have getNodeAt. We want to pass an index. So now this one is really to show you that, let's say for array, if I want to go to index 0 or index 1, it's going to be a constant operation, right? But now for getNodeAt, it's not. For example, let's say if I say list.getNodeAt1, index 1, I want to get, for example, Mark. So what I should do is I should initialize some counter there and then keep counting until I get to position 1. So what would be the worst case? Worst case would be I say list.getSize and then pass the last position there, in which case you got to take that many next references, right? Okay, as your exercise, I think you're ready to really study this by yourself. Okay, it's going to be very, very similar to what we did before. Very, very similar. Okay, if you got trouble, feel free to talk to me, okay? Very similar. The only thing is we got index over here. That's going to record when we should exit, okay? Well, I'll leave that to you. And then I also got tracing over here you can go through. Okay, worst case is when you get to the last position, right? So that's really the worst. Again, this is expensive for the linked list, but very cheap for array. I want to finish 5 minutes earlier today because I got something else to do very quickly. So, but let's go for another 5 minutes. I want to go as much as possible. Okay. So now, let's say how to do this. Let's think about conceptually. Let's say I want to add a node at position I. Okay. For example, let's say this. Let me give you an idea. Okay, we get node, I'm going to let you study that. addAt. Okay, so now let's say I say list dot addAt. Let's say this is position 0, position 1, position 2. addAt position 1, and then I want to add Jim. So what I really want to have is I want to create a new node over here, and then element is going to be Jim. And then the next, somehow I'm going to set it, right? What I want to have is, now after this method call, the node containing Jin should become at position 1, which means I should have, let me just use a different color here. Rather than here, I'm going to have over here, and then this should point to over here. Okay, so now, can you imagine what the complexity of this method should be? Depends on the size. Whenever you say depends on the size, because the I over here I'm confusing you, I'm just using 1. What if is maybe the last index? In that case, you have to get a 1 before that, and then set the next. Okay, so now, this is, I'll give you a hint when you read the code. So this is exactly, this is I. You have to go to the node at position I minus 1. Get there and then set the next to be a new node. Okay, that's a hint to you. Okay, when you study that, hopefully you will just get it. Okay, now, inserting to the middle, okay, and now the complexity will be, so one thing I want to show you is, remember we defined the getNodeAdd method just before, so we can now use it as a helper method. Okay, we're just calling that. So now this actually illustrates one point which I said in the big O notation. If you try to analyze this code here, what would that be? Complexity. Constant or linear? But there's no loop. No loop here, right? Well, it's because in line number 10, the getNodeAdd takes linear time. So that's why I make a remark before. Why is method call not a primitive operation? Because it can be linear, it can also be even exponential, right? In this case over here, in line number 10, the getNodeAdd takes linear time. It's going to dominate every step. Okay? Okay, getting there. Okay, now you can also remove the last. Okay, now how do we remove the last? Well, we have to go to second last, right? Okay, you will see that. Okay, we just go to the second last, right? getNodeAdd second last, which will take also linear time, and then set the references accordingly. Okay, I'll let you study that as well. Again, the reason that I'm not trying to be lazy on you, I'm just trying to say now you have got enough ground to really study this. You really have to visualize yourself how the methods work. That's really important. Okay, that's also linear time. So now I'm going to leave some exercises for you over here, and then I will talk about this exercise particularly. Guys, just 1 minute. Okay, the reason I finished 5 minutes, let me just tell you what you should do. Okay, let me